The F-35 Lightning II. It's not just a fighter jet. It's one of the most expensive and technologically ambitious weapon systems in history. A flying supercompute, a quarterback in the sky, able to see everything, share everything, and destroy targets with stunning precision. It's designed to be the undisputed king of the air for decades. But what if the very thing that makes it so dominant, its incredible suite of electronics, is about to become its greatest weakness? What happens when the most advanced jet in the world simply runs out of power? There's a crisis brewing in the F-35 program, a fundamental limit that no software patch can fix. The jet is hitting a wall. And across the Atlantic, the legendary engineering firm Rolls-Royce has built a radical solution, a new type of engine core that could offer a staggering amount of electrical power. It's the kind of leap that could enable a new generation of warfare, powering weapons straight out of science fiction. But bolting this revolutionary power plant into the F-35 would have a shocking, paradoxical consequence, one that could leave the world's most advanced fighter powerless and literally out of fuel in the middle of a fight. To understand this crisis, you have to understand what the F-35 truly is. Forget the classic image of a dog-fighting jet twisting and turning in a dance of raw horsepower. The F-35 is different. It's a node in a vast, invisible network. Its power comes from information. Its skin is a network of antennas. Its nose holds a radar of almost clairvoyant power. And beneath the pilot, a humming rack of processors fuses data from every sensor on the jet and every other friendly asset in the area into a single coherent picture of the battlefield. It might see an enemy missile site from hundreds of miles away, not because its own radar picked it up, but because a satellite, a drone, and another F-35 50 mi away all triangulated its position and streamed that data right to the pilot's helmet. This is sensor fusion, and it's what makes the F-35 a fifth-generation fighter. It's a capability that has made it one of the most sought-after fighter jets in the world. At the heart of this machine, providing both the brute force to punch through the sound barrier and the electrical lifeblood for its digital brain, is the Pratt & Whitney F-135 engine. And make no mistake, the F-135 is a marvel of engineering. A direct descendant of the F-119 engine that powers the legendary F-22 Raptor, the F-135 is the most powerful fighter engine ever put into service. At full afterburner, the F-35A's engine can generate an earth-shattering 43,000 lbs of thrust, enough to push the jet to supersonic speeds, and in the case of the F-35B variant, to literally hover in midair. But the F-135 does more than just produce thrust. It's also a power plant. A component called the Integrated Power Package, or IP, taps into the engine's main shaft to generate electricity for the jet systems. The radar, electronic warfare suite, cockpit displays, and more. For years, it has been enough, but the future is arriving faster than expected. The Pentagon's ambition for the F-35 is wrapped up in a massive multi-billion-dollar upgrade program known as Block 4. This isn't just a software update. Block 4 is a complete overhaul of the jet's combat capability meant to keep it ahead of threats from China and Russia. It includes a new, more powerful radar, a vastly more capable electronic warfare system, and a new core processor to handle the tsunami of data that these new systems will generate. And here's the catch. Every single one of these new electronic systems demands more electrical power, and every watt they consume generates heat. Lots of it. And the F-35, a marvel of compact, stealthy design, is running out of both. The F-135 engine and its power and thermal management system designed decades ago are being pushed to their absolute breaking point. According to government watchdog reports, the current power and cooling system is already stressed just to handle existing electronics. The system is running so hot that it's causing extra wear and tear on the engine. The planned Block 4 upgrades will demand even more, creating what program officials call a power and thermal management crisis. It's a hard wall of physics. You can't just install a more powerful computer if you can't supply it with enough electricity or keep it from melting. The upgrades are being held back not by a lack of ambition, but by a lack of watts and a surplus of degrees. The problem has become so severe that the Block 4 program has been hit with major delays. Capabilities that depend on a new power system have been pushed back, some potentially as far as 2033. The digital predator is being choked by its own insatiable hunger for power. For decades, the currency of air combat has been kinetics, missiles, and bombs. But the future may belong to something far more revolutionary: directed energy. This is the realm of weapons that travel at the speed of light with a nearly infinite magazine, limited only by the amount of power you can generate. Imagine a high-energy laser on a fighter jet. Instead of firing a missile to intercept a drone, the F-35 could just point its laser and incinerate the threat in a fraction of a second. No expensive missile spent, no need to reload. The only limit is the flow of electricity. We're talking about solid-state lasers in the kilowatt and eventually megawatt class. While still largely experimental for fighters, a 1 megawatt laser is in development and could theoretically disable ballistic missiles. Then there are high-power microwave weapons. These systems don't burn targets, they fry their electronics. By emitting a powerful, focused beam of microwave energy, a fighter could disable swarms of drones, overload the guidance of incoming missiles, or shut down an enemy network without firing a shot. These aren't just defensive tools. They're offensive weapons that could dominate the invisible battlefield of the electromagnetic spectrum. But this dream of energy warfare runs headfirst into the F-35's power crisis. The current F-135 engine generates a respectable amount of electricity, but it's measured in kilowatt. Directed energy weapons require megawatt. A single megawatt is 1,000 cow. To power a weaponized laser, the F-35 would need a power source far beyond what its current engine can provide. It's like trying to power an industrial smelter with a handful of car batteries. The power problem extends beyond just weapons. The future of air combat is worked and collaborative. The F-35 is envisioned as the quarterback for a team of uncrewed loyal wingmen, or collaborative combat aircraft (CCAs). These drones will fly alongside the manned fighter, acting as its eyes, shields, and extra arsenal. They can fly into the most dangerous areas, jam enemy radar, launch their own weapons, and feed sensor data back to the F-35 pilot. Commanding this robotic swarm requires an exponential leap in processing power and data linking. The F-35's core processor has to crunch terabytes of data in real time, running complex AI to coordinate the drone's actions, all while managing its own systems. This level of computation consumes enormous amounts of electricity and generates a crippling amount of heat. This is the strategic dilemma facing the Pentagon. The F-35 must evolve to carry these next-generation systems, or it risks becoming obsolete. The Air Force of the 2030s and 2040s won't be defined simply by speed and stealth, but by its energy budget. The fighter that can generate the most power, manage the most heat, and wield the most advanced energy weapons will rule the sky. The F-35 in its current form is not that fighter. It needs a new heart. While the F-35 program grapples with its power and thermal ceiling on the other side of the Atlantic, Rolls-Royce has been quietly revolutionizing the jet engine. For years, their engineers have been working on a sixth-generation power system, seeing it not just as a means of propulsion, but as an integrated power and thermal management system. The result of this research, which began as far back as 2014, is a new engine core demonstrator that represents a quantum leap in technology. The headline-grabbing claim is that this new core architecture can generate a massive amount of electrical power, potentially mega WW. Where the F-35 struggles to supply the kilowatts needed for its Block 4 upgrades, Rolls-Royce is talking about generating enough electricity to power roughly 2,500 homes. It's a staggering amount of power aimed squarely at the demands of the future: directed energy weapons, advanced AI, and commanding drone swarms. The secret lies in a key innovation: the Embedded Electrical Starter Generator, or EESG. In a conventional jet engine, a heavy complex gearbox mounted to the outside of the engine spins a separate generator. This system is inefficient, adds weight, and is bad for stealth. Rolls-Royce's EESG gets rid of the gearbox entirely. They've engineered a powerful, compact generator that is integrated directly into the core of the engine. This more electric architecture is not only lighter and more space efficient, but it's also vastly more powerful. But massive power generation is only half the equation. More power means more heat. Rolls-Royce understood this from the start. Their new core isn't just a power source, it's also a heat sink. The architecture is designed to manage the extreme thermal loads from next-gen electronics. It can pull waste heat from the jet systems and manage it within the engine's own thermodynamic cycle, simultaneously powering and cooling the mission systems. This revolutionary engine core isn't just a science project. It is the beating heart of a real next-generation fighter program, the Global Combat Air Program, or GSAP. This is a massive multinational effort by the UK, Italy, and Japan to develop their own 6G generation stealth fighter with a target service date of 2035. The aircraft, sometimes known as Tempest, is being designed from the ground up to be a worked AI-enabled energy-dominant fighter meant to replace the Eurofighter Typhoon and the Japanese F-2. The GSAT program represents a major strategic move. By pooling their resources, the UK, Italy, and Japan are creating a direct competitor to the United States' own secretive Next Generation Air Dominance, or NGA, program. They are building an advanced fighter that isn't reliant on US technology, providing a powerful alternative for nations looking to acquire sixth-generation capabilities. Rolls-Royce and its partners are building an engine not just to win dogfights, but to reshape the geopolitical landscape of military aviation. This level of engineering is rewriting the rules of air combat. The jet engine is evolving from a propulsion system into the integrated power plant of a flying supercompute. If you find these deep dives into military technology fascinating, make sure you're subscribed so you don't miss our future investigations. Now, we've established the F-35's critical power problem and Rolls-Royce's revolutionary solution. So why not just put this incredible new engine into the thousands of F-35s already flying? This is where the shocking paradox comes in. Even if you could, the result would be a fighter that is simultaneously the most powerful and the most vulnerable it has ever been. So we have a power-starved F-35 and a megawatt-class Rolls-Royce core. The solution seems obvious, but aerospace engineering is never that simple. The first hurdle is just brute physical reality. The Rolls-Royce GCAP engine core is not a Lego brick. It's a clean sheet design for a completely different aircraft. The F-35's airframe, especially the incredibly complex F-35B with its vertical lift fan, is one of the most tightly packaged designs ever created. The F-135 engine is woven into the very structure of the aircraft. The Rolls-Royce core, with its different dimensions and architecture, simply does not fit. Retrofitting it would require a complete redesign of the F-35's fuselage. A task so colossally expensive, it would be like designing a whole new aircraft. But let's do a thought experiment. Let's imagine we could seamlessly integrate a 2-megawatt power system like the one Rolls-Royce is pioneering into the F-35. The jet now has all the power it needs for Block 4, advanced AI, and even a powerful laser. Problem solved, right? Wrong. This is where we hit the paradox of power, rooted in the unbending laws of thermodynamics. Electrical power on a jet isn't free. It comes from converting the rotational energy of the engine's main shaft into electrical energy. The more electricity you draw, the more mechanical load you place on that shaft. Think of it like the alternator in your car. When you turn on your headlights, stereo, and AC, the alternator works harder, and the engine has to burn a little more fuel. On a fighter jet, this effect is magnified enormously. To produce a certain amount of thrust, the engine must burn fuel at a specific rate. Now, let's say our hypothetical megawatt-powered F-35 pilot gets into a fight. He needs to power his next G-jammer, run his combat AI, and for 10 seconds fire a 1 megawatt laser to disable an incoming missile. That 1 megawatt draw is an immense load on the engine. To compensate for this massive energy extraction, the engine's control system will do the only thing it can: pour more fuel into the combustor, a lot more fuel. The jet might win the immediate engagement. The laser works perfectly, but the pilot looks down at his fuel gauge and sees a terrifying sight. The needle has dropped. Those 10 seconds of laser fire have consumed an amount of fuel that could have let him cruise for several minutes. His combat radius, the distance he can fly to the fight and return, has been slashed. This is the shocking consequence. You've given the F-35 an infinite magazine of light-eed weapons, but only enough fuel to fire them a handful of times before it's dangerously low on gas, hundreds of miles inside hostile territory. The very weapon that ensures your victory in the engagement could be what causes you to lose the jet. It runs out of fuel, not because of a leak, but because it's using its own power. The more power it uses, the faster it bleeds its most precious resource: mission endurance. The title of this video isn't just clickbait. It's a simplification of a profound engineering truth. A massive power upgrade of the kind Rolls-Royce is developing would fundamentally change the F-35's metabolism. It would transform it into a sprinter capable of astonishing bursts of energy, but at the cost of the endurance it needs to get to the fight and back. So, if the revolutionary Rolls-Royce core isn't a viable option for the F-35, what's the real solution? The Pentagon, faced with the physical and financial impossibility of a full engine replacement, has opted for a more pragmatic path. The answer is the F-135 Engine Core Upgrade, or ECU. This program, led by the original engine maker Pratt & Whitney, modernizes the existing F-135 engine rather than replacing it. The ECU isn't a 10x power leap. It won't enable megawatt-class lasers, but it is designed to provide the crucial extra power and cooling to safely operate the F-35's Block 4 upgrades. It's an incremental but essential improvement that works within the current airframe and is compatible with all three F-35 variants. It's the sensible, cost-effective solution to keep the F-35 fleet relevant. The ECU is on a timeline to be ready for the fleet around 2029, though, as with many large defense programs, timelines can shift. There was a more ambitious option considered: the Adaptive Engine Transition Program, or AETP. These revolutionary engines can alter their airflow to switch between high thrust and high efficiency modes. However, the Pentagon decided against it for the F-35, citing immense cost and complexity. The technologies from AETP aren't being wasted, though. They're being rolled into the next-generation Adaptive Propulsion NGAP program, which is developing the engines for America's own sixth-generation fighter, the highly classified NGA platform. This points to the real future of air power. The kind of megawatt power that Rolls-Royce is pioneering with its GCAP engine and that the US is pursuing with NGAP is destined for new airframes. Sixth-generation fighters like NGAD and GCAP Tempest are being designed from the ground up with energy warfare in mind. They will almost certainly be larger than the F-35, with bigger fuel tanks and more advanced thermal management systems. They are being conceived as energy-optimized platforms where the engine, airframe, and weapon systems are co-designed for a sustained high-tech fight. The F-35 will continue to be the backbone of Western air power for decades. With the engine core upgrade, it will get the power it needs for its critical Block 4 enhancements, but its role may subtly shift. The F-35 will be the versatile workhorse, while the new, larger, more powerful sixth-generation jets become the specialized silver bullet assets, flying into the most contested airspace, wielding lasers, directing drone swarms, and dominating the electromagnetic spectrum. The story of the F-35's power crisis is a window into the next great revolution in military aviation. The world's most advanced fighter, a testament to digital power, has hit the physical limits of its own design. Its voracious appetite for processing power has created a power and thermal shortfall that threatens its future. Across the ocean, Rolls-Royce has engineered a solution that seems almost too good to be true. A new engine core with immense power, purpose-built for the energy-hungry weapons of tomorrow. But this power comes with a hidden, paradoxical cost. The fundamental physics of jet propulsion mean that every kilowatt of electricity is paid for with fuel. Our thought experiment reveals that simply dropping this powerful new engine into the F-35 would create a jet that could win a fleeting battle only to risk losing the war against its own fuel gauge. While the F-35 will receive a more modest practical upgrade, the true home for these revolutionary new power plants is on the horizon. Sixth-generation fighters are being designed around a new paradigm where the engine is the integrated beating heart of the entire weapon system. The future of air superiority won't be measured in speed and altitude alone, but in watts and thermal endurance. The race is on, not just to build a faster jet, but to build a more powerful,